All right, let's settle in for one of the biggest detective stories in all of science. We're going on the hunt for a suspect that outweighs everything we can see, everything we know, by about 5 to 1. It's a substance that literally sculpts the galaxies and the very structure of our universe, and yet it remains completely and utterly invisible. This is the search for dark matter.
So, to really get a handle on the scale of this mystery, you just need to look at this one number, 85%. That's how much of all the matter in the entire universe is, for all intents and purposes, missing. We can't see it. It's not stars, it's not planets, it's not the gas or dust floating between them. It is something else entirely, and figuring out what it is, well, that's the whole ballgame.
You know, the case file for this mystery was first opened because the universe just wasn't behaving the way our laws of physics said it should. When astronomers look out at distant galaxies, they see them spinning so fast they should be flying apart, but they're not. It's like some invisible cosmic hand is holding everything together with its gravity.
And, this isn't a new problem. The first clues started popping up way back in 1933. An astronomer named Fritz Zwicky saw that galaxies in the Coma cluster were zipping around way too fast. They should have just flung themselves out into deep space. Then, the case got a huge break in the 1970s thanks to the incredible work of Vera Rubin. She proved that stars on the edges of galaxies were spinning just as fast as stars in the middle, which makes no sense unless there's a giant invisible halo of matter providing extra gravitational glue.
So who or what is our prime suspect in this cosmic whodunit? For a long time now, the leading candidate has been a totally new kind of particle, something that's not in our standard playbook of physics. And get this particle could be streaming through your body right now by the billions.
So let's meet the main suspect, the WIMP. It stands for Weakly Interacting Massive Particle, and the name really says it all. The theory is that these things have mass, which is where the gravity comes from, but they barely interact with us or with light at all. That makes them massive, invisible, and incredibly hard to catch. I mean, it's the perfect profile for the culprit we're looking for.
Okay, so how do you go about catching a ghost? Well, it's not easy, and it has sparked this massive worldwide manhunt. Scientists have been building some of the most sensitive, most incredible detectors ever imagined, all to try and get just one single glimpse of this elusive particle. And this really shows the genius of their plan. Scientists are basically running a three-pronged investigation. First, there's what they call direct detection, which is basically trying to catch a dark matter particle in the act of bumping into normal matter. Then, there's indirect detection, where they look for clues left behind when dark matter particles destroy each other. And finally, there's production, trying to create dark matter from scratch in a particle accelerator.
Let's start with that first strategy, direct detection. You can think of it like setting the world's most sophisticated, most patient trap. The idea is to build a detector that's so clean, so isolated from everything else in the universe, that the only thing that could possibly set it off is a WIMP flying right through the planet and smacking into one of its atoms.
And here's what that looks like in the real world, with the absolutely incredible Lux Zeppelin experiment. First, they bury the whole thing nearly a mile underground to block out all the cosmic noise from space. At its heart is a giant vat filled with 10 tons of super pure liquid xenon. And then, they just wait. They're hoping a WIMP will barrel through and hit a xenon nucleus, creating a teeny tiny flash of light, a signal that could be our first direct proof of dark matter.
But scientists aren't putting all their eggs in one basket. They're also using those other two strategies to cover all the bases. With indirect detection, they use telescopes to scan the skies, looking for telltale signs like gamma rays that might be produced when two WIMPs collide and annihilate. And with accelerator production, they use machines like the Large Hadron Collider to smash protons together, hoping that in the debris, they might create a dark matter particle right here on Earth.
But hold on, what if we've been chasing the wrong suspect this whole time? I mean, what if there is no missing particle? There's an alternative theory out there that suggests the problem isn't missing matter at all, but a fatal flaw in our understanding of gravity itself.
So this brings us to a huge fork in the road, a real showdown between two big ideas. On one side, you have the dark matter theory, which says, let's add a new ingredient to the universe, a new particle. But on the other side, you have MOND, which stands for Modified Newtonian Dynamics. MOND says, we don't need a new particle, we just need to tweak Newton's law of gravity. It suggests that when you get to the super low accelerations you see in galaxies, gravity just works differently. It's stronger than we thought.
Okay, so we have our two main suspects, a missing particle or a broken law. Let's put on our detective hats and sift through the evidence to see which story holds up.
And honestly, one of the most powerful pieces of evidence, the smoking gun, if you will, comes from this incredible cosmic car crash called the Bullet Cluster. What you're seeing is actually two massive galaxy clusters that have smashed right into and through each other. And what astronomers found here was absolutely mind-blowing.
So here's what's so critical. During this collision, all the hot gas, which is most of the normal matter, crashed together and got stuck in the middle. But when scientists mapped out where the gravity is, they found that the center of gravity isn't where the gas is. It's way out on the sides with the galaxies. For the dark matter theory, this is a slam dunk. The invisible dark matter just passed through itself like a ghost. But for MOND? Well, MOND has a really tough time explaining why the mass and the gravity are in two different places.
But like any good detective story, just when you think you've got it figured out, the case takes another turn. A new lead has come in that complicates the picture. It's a modified version of the theory called self-interacting dark matter, or ＳIDM. And it asks a simple question. What if dark matter particles are ghosts to us, but not to each other?
And this new twist, ＳIDM, is really exciting because it might solve some of those small, nagging mysteries that the original WIMP theory struggled with. For example, it could explain why some small galaxies seem to have dense, spiky cores of dark matter, while others have these big, fluffy, spread-out cores. These self-interactions could actually reshape the dark matter halos, creating all the beautiful diversity we see out there in the cosmos.
So after all that, where does it leave our investigation? Well, the truth is, despite decades of searching, some of the most brilliant minds on the planet and these incredible experiments, the case of the missing mass remains very much open.
And I think this quote really gets to the heart of it. Even when an experiment like LZ doesn't find a WIMP, it's still doing something incredibly important. Every new result helps us tighten the net, ruling out possibilities for what dark matter could be. It's progress by elimination, and that's a huge part of how science works.
And that leaves us right here with the ultimate question. Is the solution to this profound cosmic mystery a brand new particle of nature, just waiting for us to find it deep underground? Or is the answer even bigger, that we have to fundamentally rewrite our understanding of gravity, one of the most basic forces in the universe? The search, for now, continues. If you had fun playing Cosmic Detective with us today, do us a favor and hit that like button. And be sure to subscribe for more explainers just like this one. Thanks for tuning in.